Hello, everybody. Welcome back. Three likes already. The class hasn't even started. Incredible. Navik, smash the like button like the Incredible Hulk. Who comes up with this? So everybody say hi. Say hi if you're here. Good morning, Jax. Hello, Jared Turner. Right on time. Hello, Reagan. Hello, Ellie. So we'll get started in about a minute. People must be sleeping in today, it seems like. All right, well, it's 10 o'clock, so we can get started. And to get started, you don't need much. All you need is your coffee, your water, your tea, your juice, who knows, to participate in the simultaneous sip. All right, ready, go. Good stuff. All right, so the plan for today is to finish up, the plan for today is to finish up 4.5, and then tomorrow will just be a review, right? Because we got our test on Friday. See, a few of you have sipped, that's nice. All right, I hope all your classmates watch this video later. We got 9 people in the chat right now out of a class of 36. So if you have any of your classmates' phone numbers, text them and tell them to make sure they watch this. Especially U-Substitution. This is some of our hardest material. All right, so I'll write out a few examples as a warm-up. And then we can get to a harder one. All right, so the first one is find the integral of x over the square root of 1 minus 4x squared dx. And then the next is evaluate the integral of cosine of 5x dx. All right, and I guess I could write out one more, which will be the hardest of the 3. So the last one is evaluate or find I mean, I'm not sure why I switched between find and evaluate. They're the same. They're asking the same thing. Find the integral of the square root of 1 plus x squared times, so x to the fifth is outside of this square root. So times x to the fifth dx. All right, so I'll give you a few minutes to try to work on these. They all involve U-substitution. And since I can't like see your work, do you want to maybe in the chat write out like question 1, U equals blank, and I can tell you if you're on the right track or not. You know, maybe U equals whatever and DU equals whatever DU would be. Yeah, so for the first one, I think that's a good idea, Jax. Try U is equal to 1 minus 4x squared. So U could be the inside of the square root. And DU will be negative 8x. So we already have an 8. I mean, we already have an x here. So somehow you have to get a negative 8. James agrees. Has anybody thought about question 2 yet? Yep, Jared and Ellie, I like what you're thinking. U equals 5x for that one, and then DU would be just 5 dx. Bono, you're close on that first one. You're real close. What are you missing? Again, real close on the second one, but you're missing something. Jared sees it. All right, good. So let's do these first two together. These ones are quick. Then, and if you got these first two, you know, mute me and think about this third one. Those of you who watched my YouTube video from yesterday should at least have the right, know how to get started on this one. Okay, so we could let U equal, it's always a good idea. We don't really know how to deal with square roots. You'll learn in Calc 2, which I hope some of you take, how to deal with integrals of square roots if U-substitution doesn't work. But at this point, our only technique is to hope U-substitution works. So we'll let U equal 1 minus 4x squared, which tells us du is equal to minus 8 dx, or another way to say that is dx, sorry, minus 8x dx. We have an x dx, so that tells us that x dx is equal to du over negative 8. So our integral is negative 1/8 the integral of 1 over the square root of u du. So what do we do? How do we integrate 1 over the square root of u? How should we rewrite it in order to see that it's actually pretty easy to integrate? You don't have to type it out. Just say out loud to your laptop how to do that. I don't want to wait for the delay, so I'll just write it out. Okay, so you express it as u to the negative 1/2. So we'll add 1 and divide by the new power. You got to remember the plus c. That's free points. Think about that. You're obviously going to have on the test on Friday, you're obviously going to have to evaluate some integrals. And so if you have indefinite integrals, that's free points right there, the plus c. So make sure to remember that. And then we want to switch back. We started with x, so we should end with x. So this is equal to, well, negative 1/8 divided by 1/2 is negative 1/4. And we switch the u back to how we started. All right, so let me see in the chat, thumbs up or thumbs down about question 1. While you're typing that in, we can work through question 2. I saw some of you said we should use u equals 5x, which is a great idea. Basically, it's always a good idea to have u be the inside function. So here our inside function would be 1 minus 4x. Here it's 5x. So du is equal to 5 dx, or dx is equal to du over 5. And so our integral is really 1/5 the integral of cosine of u du. The integral of cosine of u is sine of u. Plus c. And then again, I know some of you are going to just stop here, and that's not how we're going to do that. Hold on. Did I make a mistake somewhere? How did the x turn into the 1 in the integral? I'll get in the first one, Jared. I'll get to that in a second. We want to switch back. We started with x's, so let's end with x's. Okay, so in this first one, we had du is negative 8x dx. What we're given here is x dx. Right? So we solved for x dx. So we can replace x times dx with du over negative 8. Okay, so this thing groups together, pairs up to give us du over negative 8. And so then when we do that substitution, well, we could have had du in the numerator, but instead I put it on the side because it looks better. But yeah, that's where it went. Okay. Got it? All right, thanks. Yep. What about this last one? Anybody have any luck with this last one? Banu says thumbs up. Good, good. What's a good guess to use for you here? X to the fifth. Yeah, but how are we? We don't know how to integrate 1 plus x, the square root of 1 plus x squared yet. Okay, let's see. Jax, I like your idea. Navik, I also like your idea. Let's have u be 1 plus x squared and see what we can do from there. Okay. So u is equal to, let's try 1 plus x squared. So du is equal to 2x dx. Okay? Our integral, before we even switch to the u's, you know, if we're planning this route of attack, we should break up our x to the fifth into an x to the fourth times an x to the first. And the reason we're doing that is so we could group together an x dx, which will become du. All right, and while we're at it, let's multiply by 2 and divide by 2. Right, so before we do the substitution, this will become u, right? Square root of u. This will become du, and we're left with an x to the fourth that we're not sure. We're not sure what to do with it. So maybe we're out of luck, and I just gave you a question that was too hard. Maybe this was also a test to see which one of you guys use integral calculators on your test, which you shouldn't use. So let's see what we can do. We have u is equal to, so let's take this equation. So I guess the question is, what does x to the fourth equal in terms of u's? Well, okay, so Jax asks, could you not break down x to the fifth into x squared times x to the third? Well, we definitely want to group one of the x's with the dx, right? That's a no-doubter based on this first line. Du is equal to 2x dx. We need one of the x's from this x to the fifth to be with dx. Okay, and so now the question is, how do we deal with this x to the fourth? Well, let's see. And Jax, I think you're on the right track. We could break up x to the fourth into x squared times x squared, and we could solve for x squared in terms of u. Using this equation, x squared is equal to u minus 1. Which tells us that x to the fourth is, yeah, what Banu said, u minus 1 squared. Okay, and so now we know how to express each part of our integral in terms of u's. So our integral is 1/2 the integral of the square root of u times u minus 1 squared du. But this doesn't, well, it actually it helps, but where do we go from here? We don't know how to integrate a product. Yeah, well, FOIL and distribute or expand, yeah. So instead of writing it as u minus 1 squared, let's write it as u squared minus 2u plus 1. And now we can distribute the square root of u to each of the terms. And this is an integral that we know how to evaluate. So I'll just leave the 1/2 on the outside. We can deal with that at the end. So for each of these, increase the power by 1, divide by the new power. Okay, and now we can just, I mean, this is a fine way. Oh, well, it's not a fine way. I'll leave it. We can multiply this 1/2 through, and it's going to kill all the 1/2s in the denominator. So this is u to the 7/2 over 7 minus 2 u to the 5/2 over 2 plus u to the 3/2 over 3 plus c. Okay, how do we finish the question? Yeah, so we started with x's, so we should end in x, right? We don't want to, our answer, our final answer should not be with u. So that's 1 plus x squared to the 7/2 over 7 minus 2 times 1 plus x squared to the 5/2. Sorry, this should be over 5. Over 5 plus 1 plus x squared to the 3/2 over 3 plus c. Okay, and this is about as hard as it's going to get when it comes to integrals for this class. Calc 2, maybe this would be one of the easier ones. But for this is about as hard as you'd see a U substitution question. Where did du go? We evaluated the integral. If you're asking in this line. Yeah, so when you evaluate the integral, du tells us which variable to take the integral with respect to. All right, so does anybody have any questions about this example? If you want to see another example that's similar to this, take a look at the video I posted yesterday on YouTube. Benedict Stevens smashes the like button like the Incredible Hulk. You love to hear that. All right. So let's take a look at another type of problem. So far with our U substitution, we've been doing indefinite integrals. But you could imagine I could ask you to evaluate a definite integral that requires U substitution. And so we'll talk about how to deal with the bounds, right? Our boundaries are just originally are in terms of the variable x. But when we switch variables, the bounds are going to switch as well. So we'll talk about how to deal with that. Okay? All right, so the theorem says, again, it's the same setup as we had yesterday. If G prime is continuous, on AB, and F is continuous on the range of G, again, not terribly important, just you're allowed to take their composition. Okay, so then here's the important part. The integral from A to B of f of g of x times g prime of x is equal to the integral of g from g of A to g of B of f of u du. Okay, so what does this theorem say? It says if we do U substitution, we change the bounds, and the way we figure out what the new bounds are is we just plug them into our U substitution. Okay, so if we started off going from, let's say, 0 to 1 in this integral, we'd plug in 0 into here, and that would be 1. And then we'd plug in 1, and we would get 2. We'd go from 1 to 2 instead. Hopefully it's clear with an example that we're not really doing anything crazy here. Okay. So let's look at an example. Evaluate the integral from 0 to 4 of 2x plus 1 dx. Okay, so in the chat, I want to see what are you going to use as u, what is your new lower bound, and what is your new upper bound? So you square root of x. For u, well, we don't have a square root of x as one of our terms. Right? So maybe it'd make more sense to try using the inside function. Yeah, so try using 2 plus x. But if we use 2 plus x as our function, now it seems like a few of you put 2 plus x, great. What's the new lower bound and what's the new upper bound? So what you would do is you would evaluate 2 plus x at each of these bounds. So you'd plug in x equals 0, what do you get? Plug in x equals 4, what do you get? And those are our new bounds. Yeah, so I see a few of you have it, 1 and 9. So since you switch, wait, is it 3? No. So you don't evaluate the square root, Jared. Oh my gosh. Molly's correct. You keep saying 2 plus x. It's 2x plus 1. Yeah, you're exactly right. 2 plus x was from my YouTube video yesterday. 2x plus 1. Sorry, so Jared, you're probably confused with me misspeaking. U would be 2x plus 1, like you all said. And then you evaluate the lower bound at 2x plus 1 and the upper bound at 2x plus 1 to get the new ones. All right, so let's work this out before I keep saying ridiculous things. Okay, so u is equal to 2x plus 1, like you all said. Du is 2 dx. So dx is equal to du over 2. U of 0 is equal to 2 times 0 plus 1, which is 1. And u of 4 is 2 times 4 plus 1, which is 9. Okay, so our integral is the integral from 1 to 9. Okay, now something to be careful about is it's not always going to be the case that the smaller number is going to be on the bottom. The number that goes on the bottom is the number that came from the number that was originally on the bottom. Okay, so maybe our integral would look funny with the numbers reversed, but it's still going to give us the right answer. So integral from 1 to 9 of the square root of u du, which is u to the 3 halves over 3 halves, evaluated at 1 and 9. So we don't have to switch back. Since we switched our bounds, we don't have to switch back. We keep it in u's. Okay, and so that's 2/3 of 9 to the 3 halves minus 1 to the 3 halves. Okay, hold on. Who wants to catch my mistake? This question, oh, Rena got it. I've been all over the place in this question. Yeah, dx is du over 2. You all saw it. My bad. So the 1/2s cancel. And we're left with 9 to the 3 halves is 27. 1 to the 3 halves is 1. So this is 26. over 3. Yeah. So when you watch this video on replay, I'm going to edit out this whole question. No, I'm kidding. You know, that's the beauty of live TV is mistakes happen. Live YouTube, I should say. All right, let's look at another one. If you decided to replace U, okay, this is a good question. So draw your attention to the chat. If you decide to replace U with 2x plus 1 and then evaluate the definite integral, would the bounds return to the original ones? Yes. So if you don't want to worry about the bounds, let's say you kind of, you say, I'll just deal with the bounds at the end. I don't want to worry about switching them. Then just ignore the bounds, do the integral, switch it back to x, and then you can plug in the original bounds. Okay, so if you prefer not touching the bounds, if you prefer not switching to the coordinates u with the bounds, then just switch back to x after this step, and then you could use what we started with. All right, let's look at another example. I guess before we get to this example, so typically I like to have 2 days of review before a test, but we don't have that much time, obviously, because the test is on Friday, and we're not really reviewing right now. So would anybody be interested in having like a live office hours tonight, like we did before the first online test? So if I were to have live office hours tonight, where we just go through the review questions, that I posted to Canvas, would anybody actually show up? Okay, I got a few yeses. Okay, Dab, use. Okay, good. So 6 o'clock is what we did last time. So we plan 6 to 7 again. Let's plan on 6 to 7 Eastern. See how it goes. I'll send out an email with a link. But take a look at the questions beforehand so you know which ones you want to go over. There's quite a bit of 26 questions or so. Okay, so it's on video, so it's got to happen now. All right, evaluate the integral from 1 to 2 of dx over 3 minus 5x squared. I guess let's write it how we'd see it. All right, let's see if I could go this whole question without saying something wrong or ridiculous. So let me see in the chat what you would use for u and what our new bounds are. Good, Greg. And Navik. Yeah, so u would be 3 minus 5x. And what about our bounds? All right, seems like a few of you have it. So let's work this out. So we said we'll let u equal 3 minus 5x. So du is minus 5 dx. So dx is du over negative 5. Don't let me forget this, all right? I did it last time. I forgot the negative. All right, I forgot the 1/2 last time. Let's not forget this doesn't look anything like a negative 5. Let's not forget that. So our lower bound is 3 minus 5, negative 2. Our upper bound is 3 minus 10, which is negative 7. So notice that our lower bound is larger than our upper bound, and that's perfectly fine. So our integral is minus 1/5. Okay, got that. The integral from negative 2 to negative 7 of 1 over u squared du. All right, so increase the power by 1, divide by the new power. So the new power is negative 1, so we'll have a negative and a negative. Those cancel. So this would be a fine way to leave your answer, but if you want to clean it up a bit, it's 1/5 times 7/14 minus 2/14, which is 1/5 of 5/14, which is 1/14. All right, so let me see a little feedback in the chat if you're happy with this question. But I think we could move on to our last theorems of the semester. Our last theorem of the semester. Like this if you cry every time. All right, enough of that. This is how we integrate symmetric functions. Okay, as in not symmetric functions, but functions that are that are either even or odd. Okay, so we have a function that's continuous on the interval of negative a to a. Okay? So the theorem has two parts. If f is even, then the integral from negative a to a is equal to, well, what's it mean to be even? It means it's symmetric about the y-axis. So everything on the right-hand side of the graph is the same as it is on the left-hand side of the graph. So if we want to go from negative a to a, we could just go from 0 to a and then double it. Okay, and 2, if f is an odd function, well, that means everything on the right-hand side is negated on the left-hand side, right? It was symmetric about the origin. So the integral from negative a to a of f of x dx. Well, if all the positive terms are canceled out with all the negative terms down here and vice versa, this integral is just going to be 0. Yeah, so Jax asks, are we checking symmetry before integrating? So this theorem is, I mean, if you see a question on the test or the final where you're integrating from negative something to the positive version of it, and it's just like a function that you don't know how to integrate, then chances are you should check for the symmetry and see if you could use one of these theorems. Okay, and we'll do an example right now to see, how this could show up. So you don't need to check symmetry before integrate. Oh, so are we checking before or after? Well, chances are we wouldn't know how to integrate. So we would do it before, and then we could use one of these theorems, one part of the theorem. Okay, so note tan of x is an odd function. Okay, I don't know if we ever actually discussed that in class. So just note that it's an odd function. Evaluate the integral from -1 to 1 of tan of x over 1 plus x squared plus x to the 4th dx. Okay, and so you would look and you see, oh, our integral goes from -a to a, and it looks like a monster. So we have, I have no clue how we would actually integrate this. So what we should do is we should check to see if our function is even or odd. And then maybe one part of the theorem will help us evaluate this. Okay, so we'll say f of x is equal to tan of x over 1 plus x squared plus x to the 4th. How do we check for evenness or oddness? How do we check for the parity? We evaluate f of negative x. Okay, and this is equal to, well, tan is an odd function, so we could pull out the negative. And negative x squared is the same thing as x squared. Negative x to the 4th is the same thing as x to the 4th. So this is equal to negative f of x. So what can we say if f of x, if f of negative x is equal to negative f of x? Why can you just pull out the negative from tangent? Because tangent is an odd function. So in general, you can't do that, but with tangent in particular, you can. We didn't really discuss it in class with tangent, but yeah, it is a function where you could just factor out the negative. It's an odd function. So since f of negative x is equal to negative f of x, f is odd. So the integral from -1 to 1 of tan of x over 1 plus x squared plus x to the fourth dx is equal to, well, let's look at the theorem. If f is odd, then this integral is equal to 0. Amazing, isn't it? We didn't even have to evaluate any sort of integral. We just have this property about symmetry. All right, well, that was nice. So we'll have live office hours tonight. I said, what, 6 o'clock? So we'll go from 6 to 7, just working on those problems that I posted on Canvas. And then tomorrow morning, we'll do the same thing. Just crank through some of those problems. And then Friday, you know, I like when you guys do well on the test because it makes it easier to grade. So we got a couple of dabbers in the chat. Excellent. Yeah, so see you tonight at 6. I'll stay around to answer any questions. Make sure, as my friend Navik says, smash the like button like the Incredible Hulk before you get out of here. All right, but yeah, I'll answer any questions. So if you have questions about anything in the chat, feel free to ask. Wow, a lot of dabs. All right, well, if there's no last questions, I will end the stream. Bye-bye.